Good morning, everybody. Here we are with part 3 of the Enolates chapter. And we're going to start by investigating some different bases that we can use. So this one here is LDA. And it's probably a good idea to just get used to thinking of LDA as a strong, bulky base. It stands for lithium diisopropyl amide. So that means that it's got two isopropyl groups on a nitrogen that's negatively charged. Lithium's just the counter ion, so we usually don't use that. We usually use this part to show that this will grab one of the acidic alpha hydrogens. So you can see that this one is going to, let's say any of these 4 hydrogens can get deprotonated, and this is symmetrical. So let's say LDA grabs one of these, and then that hydrogen makes a negative charge there. And so once we have our enolate, then we see that we're using an alkyl halide in the next step. And this will just happen as an SN2 type reaction where it just attacks right there the alkyl group. And then we'll get our product, which is the alpha alkylated ketone. And it could be an aldehyde as well. In this case, it's a ketone. All right, so let's highlight what was changed. We had a ketone here, and it's got this alpha position, and now we've got an alpha alkylation. So alkyl group is what R stands for, so some kind of carbon alkyl group. So let's say this is treated again with LDA. So what will happen next? So when we look down here at this schematic from Klein textbook, it shows that there's actually 2 different alpha hydrogens here. There's one at the alpha position of the more substituted carbon, alpha carbon, and then there's the less substituted one on this side. So if we want some control over which one it reacts with, we have a choice of base and some conditions we can use. So for example, let's say we want these to react, then we want something probably bulky like LDA. So LDA would prefer to go with the red hydrogens rather than the blue one because of the steric hindrance from the R group. LDA itself, remember, it's got the isopropyl groups here, so it's going to prefer less steric hindrance. So that's why we'll see a second alkylation occurring on this side. And then for this one, we want a small, strong base. So sodium hydride is used here, where hydride is the reagent, this one right here. So sodium's counter ion. So this can come in and grab here. Or we might also use something more common than hydride, like hydroxide, methoxide, ethoxide, etc. Okay, you guys are used to these strong bases, especially in the last few chapters. So. All right, so then in that kind of case, these are considered small. So we would grab this because a small base like this will not have too much steric hindrance to come in here. Why would it want to come in here if it could always choose less sterically hindered, though? That has to do with the transition state and the idea that the enolate has a double bond. It's got a pi bond. The pi bond would there'd be 2 configurations. There'd be one where we have a pi bond that's more substituted, like here, and then there's the one where we'd have a less substituted pi bond, like this. Okay, so this is what we call the thermodynamic enolate, because this is more stable thermodynamically. Probably remember from earlier chapters about elimination reactions, how we have the Zaitsev and the Hofmann product. So Zaitsev always gives us a more stable thermodynamic product, and that's because we have 1, 2, 3 carbon groups on this double bond. But this double bond, we only have 1, 2 R groups. So for that reason, this one's more thermodynamically stable. We call that the thermodynamic enolate. And we call this one the kinetic enolate because this one can form faster, but it's not necessarily the more stable one. So in each of these reactions, you have LDA versus sodium hydride, which alpha hydrogen would it prefer, and then show me the mechanism for that. All right, so for this first one, we have the more sterically hindered hydrogen on this side, and we have the other ones over here. And so for LDA being a bulky base, it's going to prefer probably the ones that are less sterically hindered, so less steric hindrance to attack there. So I'm going to get my enolate over here, and then I can attack my alkyl halide. So don't use R. If they're actually telling you what R is, use the methyl group and show me what that is. Okay, I have a few students who are still just putting R down, but we want to know specifically what we're getting. There we go. So now you can see alkylation on this side, and for the next one, we'll have the opposite. All right, so hopefully you guys see that this one's makes the thermodynamic enolate, whereas the other one made the kinetic enolate. And that resulted in an R group being on this side, whereas this one resulted in it being on the more substituted side. So this is what we call regioselectivity, so like Markovnikov, anti-Markovnikov. So more substituted here, less substituted here. All right, now with that information, we move forward into some other kinds of molecules and doing some other alkylations. So this is probably your simplest kind of alkylation, is just have a strong base come in and attack an alkyl halide. A modification of that is to use something called a malonic ester. This one's called diethyl malonate, and with this molecule we see the more acidic and the only alpha hydrogens are right here. So we can use a base that doesn't have to be as strong as LDA. We can just use ethoxide. Or we could use hydroxide, methoxide, any of those, but we use ethoxide because we just are consistent with whatever ester we're using, in case there's substitution as well and we want to keep that group. So we just use whatever's over here. So we use ethoxide to come in, and with the diethyl malonate, you get something interesting happening. So the mechanism goes something like this. So we make the only enolate that we can, which happens to be much more acidic than just if there was one carbonyl anyway. So this is really great for that. And then once we alkylate that alpha position, notice that we're going to do that again in steps 3 and 4. So here I have step 1, I've treated it with base. Step 2, I then put my alkyl halide in, and then I'm going to treat it with base again. So when you treat it with base again, you get 2 alkylations at that alpha position, and after that you're going to do something that's sort of unusual. Somehow you can see that the product of this reaction is actually carboxylic acid. What happened to the esters and what happened to that other carbonyl group? So this is a reaction from actually last chapter with carboxylic acids. Water comes in, this goes up, eventually this comes back down, and this gets kicked out as ethanol. Okay, so we end up with a carboxylic acid after a lot of proton transfer steps. Okay, so the goal there is that we're going to make carboxylic acid. Now, when that happens, we're going to have a dicarboxylic acid. However, when you have when they're beta to each other, so there's a 1, 2, when they're 1, 2, 3, when they're in this sort of pattern right here, alpha beta, turns out that there's a resonance stabilization at this carbon that allows for one of these to cleave off. And so what happens is we end up losing one of these groups as CO2. Now they're going to keep this one, so I'll go ahead and show you how this one leaves. Okay? Now the mechanism for this is not something that you have to know, but I think it's just helpful to sort of have it in the back of your mind that this can break off as CO2 is ultimately what we're going to do. So how that sort of works is you have the lone pair here coming down, and then you can kick those up and down again, and then this bond breaks and you can sort of grab that hydrogen and pull it off if you want to. Okay, so that's going to be let's see, maybe I can draw that. Maybe it comes in this way, and then we end up with this turning into CO2 right over here. Let me highlight it for you. This will be CO2. And the H over here sort of can be used to protonate this right here. Now remember that sort of that intermediate, if you stopped, let's say you push this in, you push that up, you push that down, you can push this to the alpha carbon and make it an enolate again, and then that can just get protonated by the solvent. That also works. Okay, so anyway, we end up with CO2 lost, and we end up with just one carboxylic acid group, and then the 2 R groups. And sorry, I didn't mean to make that into an H. That's an R right there. All right, it turns out that many of the compounds that you might associate with food, like especially like stinky cheeses, we know that they have carboxylic acids in them. And in fact, during fermentation, or even when you bake bread, and there's these flavor molecules, and metabolites, from the yeast, turns out that they react to do this decarboxylation, and then we get CO2 coming out, and that's what makes the bubbles in your bread, and the holes in like Swiss cheese, for example, come from CO2 decarboxylation reactions like this. All right, so I think of this, even though it's one step, I think of it as two steps. I think of this converting to carboxylic acid with the acid and heat, and then with the heat, I can consider how it can decarboxylate. So that's how I end up with that. All right, overall, what we're doing is we're taking alkyl halides. We're still just alpha alkylating them, but it's just a little more complicated because we've got this diethyl malonate starting material. That's why we call it the malonic ester synthesis. We're not synthesizing a malonic ester. We're starting with a malonic ester, and we're synthesizing alkylated carboxylic acid. So let's see if we can apply this to the reaction up here. I want you to start with diethyl malonate and figure out what are the R groups that you need, and then apply the acid and heat in your last step, step 5. If you have 2 alkylations anyway, otherwise this will be step 3. And see what how to come up with these carboxylic acids. And let's just do one together. It's actually quite easy if you do retrosynthetic analysis. We know we're adding an R group to this alpha carbon. So here's my alpha carbon. So I chop that off. This is the R group I'm going to need of my alkyl halide. So just starting with diethyl malonate here. I need step 1, I need a strong base to deprotonate this. We usually use sodium ethoxide. Step 2, once I have my enolate, I need this group here. So I'm just going to copy that. I need this, but I need some kind of electrophile here for the enolate to attack. So that's where I have some kind of halogen, bromide, iodide, chloride, something like that. And then my last step, that's my only R group, so I'm done after acid and heat to get the carboxylic acid part right here. Okay, so that's pretty simple there. All right, so use that little retrosynthetic approach. Find out what pieces you need to glue together, and then step it through. All right, guys, for this next one, we start with the ethyl dimalonate. I see that we have... All right, guys, for this next one, I start with diethyl malonate again. I see one of the R groups is going to be this benzyl halide. So I'm going to have NaOET, sodium ethoxide, some kind of benzyl something, right? So like iodide. And then step 3 is going to have something to do with this methyl group. Now I have another R group that I have to do. So I'm going to use sodium ethoxide again. And then I'm going to get the enolate there to attack a methyl iodide. And it doesn't matter, you can use bromide or something like that instead. Number 5 is my decarboxylation because I have that. So I'm going to use H3O plus and heat to do the hydrolysis and decarboxylation. And so if I ask you on the exam, you should know how this mechanism works and what the products, this plus this is going to give me this product. You should know that as well. And the last one is we've got 2 R groups here and here. This is a carboxylic acid. This is C double bond O OH. So recognize the abbreviations. An aldehyde, by the way, is CHO. Okay, that's aldehyde, and this is COOH, carboxylic acid. So you can see what we're going to need to do. Diethyl malonate again. Step 1 is going to be sodium ethoxide. Step 2, this propyl iodide. Step 3, sodium ethoxide again. And you might ask, can I just do step 1 and step 2 and then just assume it's going to dialkylate since my alkyl groups are the same? Does it matter that I have to do 4 steps? Why can't I just assume all the enolate will form and then I just pop this in and then I'm done? Yes and no. You just want to make sure that it's completed. Once you have an enolate and it gets neutralized, then you need another base again to come in. So, and you may not want to have everything at the same time because you might also get elimination here and a lot of propene that might form. So it's better just to isolate the steps. The next reaction then, and by the way, before you move on, I would strongly recommend you write this reaction down and then write the mechanism in your portfolio, okay? And just really start learning it. Then to that, I would add this slightly modified version of what we just did. This is the acetoacetic ester synthesis. This is ethyl acetoacetate. Okay, and this molecule is basically like our other one, but how does it differ? So here we had a diester. What do we have here? We have an ester on one end and a methyl ketone on the other, because it's an ethyl acetoacetate. Acetyl group is a C double bond O with a methyl group, so acetyl group. That's the only difference. So there's no OET over here. It's the only difference. So when we end this, we get a methyl ketone. So when you want a methyl ketone, you want to start with this. When you want a carboxylic acid, you start with that. That's all. So basically, otherwise, all the same thing. So why don't you guys then give me the mechanism for that and come back. All right, guys. So for this one, I showed deprotonation, making the enolate, and then I do that. Remember, this one is preferred over this one because this one's between the two carbonyl groups. So these are more strongly acidic than these. They're more acidic than those on the other side right here. All right, so I get the enolate, and then I do the first alkylation, I do the second alkylation, and then I do that hydrolysis with the decarboxylation that chops this part off, and then I end up with just the dialkylated ketone. Again, we're using R groups of an alkyl halide, alpha alkylation of a ketone. Okay? All right, so let's try one of these together and then try the rest for yourself. So for this one, we're going to start with ethyl acetoacetate. We usually use the ethyl ester. I don't know why. We could use a methyl ester, but it's just, I don't know, we just use that the most. Maybe because ethanol is very common. I don't know. So then we use this, we get our alkylation. I need to figure out, maybe going backwards, that these are the R groups, right? So I do a little retrosynthetic analysis. So I'm going to do that here. This is an R group here. Remember, this is the alpha carbon of my original molecule. So I'm going to chop it here. So then that's going to help me figure out that I need sodium methoxide base. Step 2, I need this group right here and stick a halogen on it. And then step 3, H3O plus and heat. All right, so there we go. That's it. So I'd love for you guys to do a quick analysis of these and practice figuring out what are the starting material and reagents I need to make these methyl ketones. All right, so for this next part, I start with ethyl acetoacetate. I use the base. I use this as my R group here. This is a benzyl bromide or iodide. Then I do sodium ethoxide again, and then I have an ethyl group here, so an ethyl halide, and then the acid hydrolysis, hydrolysis with acid and heat to get the carboxylic acid, and then decarboxylate. All right, for this one here, same thing as this, except instead of this, I want maybe a butyl iodide, and here I could use an isobutyl, whatever, bromide or something like that.